Every loop you have ever written solves a problem by grinding through it one pass at a time. Recursion throws that machinery away. It solves a problem by solving the same problem, just slightly smaller. In this video, we built multiplication from nothing but addition, first with loops, then by discovering the pattern that makes the loop disappear. Start with what we already know. An iterative algorithm is code with a loop inside it, a for loop or a while loop, performing some task repeatedly. Its defining idea is state, variables that capture where the computation stands, updating on every pass. Whenever we write one, we answer 4 questions. What changes each time through the loop? A running sum is the classic example. Is there a counter tracking how many passes we have made? When do we stop? A for loop stops when its sequence is exhausted. A while loop when its condition turns false. And what result do we return at the end? To see how differently recursion thinks, we will now solve one problem both ways, multiplying 2 numbers. Here is the multiplication function we refuse to write, mult of a and b returning a star b. That is just the built-in operator doing all the work. Instead, pretend the star does not exist. Assume the only operation we know is addition. Multiplication has to be rebuilt from that alone, and the definition tells us how. Multiplying a by b means adding a to itself, b times. Every version we write, iterative or recursive, is some strategy for organizing those repeated additions. Here is the iterative answer with a for loop. The function mult takes a and b. It creates total set to 0. This is the state variable, the running sum. Then, for n in range of b, total increases by a. Since the loop runs over range of b, the body repeats exactly b times, and after the loop, we return total. Watch it run on 5 times 4. Total starts at 0. First pass adds 5, making 5. Second pass makes 10. Third pass makes 15. Fourth pass makes 20. The range is exhausted, the loop ends, and the mult of 5 and 4 returns 20. Every question from before has an answer here. Total changes each pass, n counts the passes. We stop when range of b runs out, and we return the total. Now the same job, written backward. Instead of counting up from 0, the while loop version counts down from b. Result starts at 0, playing the role total played before. While b is greater than 0, result increases by a and b decreases by 1. Here b itself is the counter, ticking down towards 0. Trace 5 times 4, result 0, b4. 1 pass, result 5, b3. Then result 10, b2. Result 15, b1. Result 20, b0. Now b is greater than 0 is false. The loop exits, and we return 20. 2 different loops, same answer. On 5 times 4, the for loop version and the while loop version both return 20. Either way, the machinery is the same. State variables, a counter, a stopping test. Managed by us, pass after pass. Now forget the loops and look at the problem itself. Recursion begins by spotting the thing being repeated over and over. Concrete numbers make it visible, so take 5 times 4. By definition, that is 5 plus 5 plus 5 plus 5, 4 copies of 5. Here is the shift. Instead of adding all 4 copies ourselves, peel just 1 5 off the front. What remains is 3 copies of 5, which is itself a multiplication. So 5 times 4 equals 5 plus 5 times 3. That is the recursive pattern. The star operator between 5 and some number became 5 plus the star operator between 5 and the number 1 smaller. We did not solve the problem. We re-expressed it as a slightly smaller version of itself. The same move works on what is left. 5 times 3 peels apart the same way. 1 5 off the front, leaving 5 plus 5 times 2. And 5 times 2 becomes 5 plus 5 times 1. Look down the lines. Everyone takes the star operator between 5 and some number, and only that number changes. 4, 3, 2, 1. Each peel makes the problem smaller, so this cannot go on forever. At 5 times 1, the problem is so easy we know the answer outright. A number times 1 is the number itself, 5. That known fact is where the peeling stops. One ladder of substitutions shows the whole structure. Start from 5 times 4 equals 5 plus 5 times 3, with the 5 times 3 wrapped in parentheses. We do not know its value yet, and that is fine. We trust that the same peel will handle it, and substitute. Inside the parentheses, 5 times 3 becomes 5 plus 5 times 2. Substituting again, 5 times 2 becomes 5 plus 5 times 1. Each replacement is legal because the two sides are genuinely equal. The boxed piece on one line is exactly what the next line expands. Now the innermost problem is 5 times 1, which we know is 5. The additions collapse outward. 5 plus 5 is 10, plus 5 is 15, plus 5 is 20. 20, the same answer the loops produced with no loop anywhere in sight. Two ways of thinking side by side. The iterative mindset runs the machinery itself, state variables, a counter, a stopping test, updated pass after pass until the answer accumulates. The recursive mindset never runs a loop. It re-expresses the problem as the same problem, slightly smaller, and keeps doing so until it hits a case whose answer it knows outright. Notice what survived the change. The repeated addition is still there, but nobody is managing it. The structure of the problem carries the computation. Those two ingredients, the shrinking self-similar step and the known stopping fact, are all recursive code needs. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.